Hi, everyone. Thanks for joining. Um, like Lisa said, I'm a professor at Brown in IBIS, the Institute at Brown for Environment and Society. I'm also in the department now called Ecology, Evolutionary, and Organismal Biology that used to be EEB back when you were there, probably. And I have the pleasure of serving as Brown's first, and actually the world's first, and the nation's first Associate Provost for Sustainability. And that means that um, the leadership decided that the issue of sustainability crossed between uh, research, teaching, and the daily life of the university and into our relationships with our community in a way that needed to be governed from, or not governed, that's a bad word for Brown because we don't govern things like that, but that need to be thought about uh, sort of holistically. And so they created this position a few years back and asked me to serve, and it's been quite an interesting ride. We now have, I think, nine in the country, eight or nine in the country, universities that have a similar position reporting directly either to the president or the provost. So Brown was out in front on this, which is kind of fun. But today I want to talk to you about a book that I wrote. It came out in the fall of 23 and paperback will be out this spring. And so I'm going to go ahead and share my screen. This is about a 40-minute talk about the ideas in the book. It's not a recitation of the book, obviously, but it's about the ideas of the book. And I hope you'll find it interesting. It's a small enough group that if you have questions, just maybe Lisa, if you could keep an eye on the chat and people could just drop them into the chat. I don't necessarily have to get through the whole thing and there's no quiz at the end. So, that's sort of up to you, but I do have a three-part story to tell you. So maybe what I'll do, unless the question is super pressing, is I'll wait till the end and then answer those questions. But go ahead and feel free to drop them in the chat as we go so you don't forget them. And I'll have an opportunity, I hope, to answer them. So I'm going to go ahead and share my screen and hope that you can see it. And let's see. Okay, so everybody can see the screen, yes? Okay, great. So let's go ahead and get started. There are the things I want to talk about today and the big ideas in the book really come in three flavors. And I think they're particularly pertinent in this moment of unprecedented in human history environmental change. So the first question coming from the ecology and evolutionary biology side is just a teeny little one, which is what is life, right? Now, obviously, this can be thought about from a religious or a uh, philosophical perspective. And I'm going to bring a particular lens to that question. Obviously, I will not answer it in full. Particular lens to that question in order to then ask a second question, which is, how is it that living things actually go about changing the world? It's actually fairly uncommon in the history of our planet for organisms to dramatically change the planet upon which we live. And interestingly, as I'll talk to you about here, they always do it in a very similar way. Uh, and it's that common thread that underpins the most successful world-changing organisms that leads me to the third part of the talk, which is really to leverage the lessons we can learn from our world-changing predecessors and ask, what does it really mean to be sustainable as an organism on this planet? And can we leverage that knowledge to help us as humans build a more sustainable future? So let's dive right in and talk about what is life. And I apologize at the outset for how simplified this idea, my answer to this question is, but it's an answer with a very specific mission behind it. So let's take a look at this photo. This is a photo of me and my daughter Phoebe. She's now first year in college, so she would be very embarrassed that I was showing this picture to everyone in the world and that it's being recorded, but if you don't tell her, I won't. This is a trip that she and I took to the Amazon when she was in fourth grade. And I show this picture because the Amazon and tropical rainforests in general are described as teeming with life. And they really are teeming with life. It's unbelievable how abundant, how verdant that world is. If you look at this picture, you see two rather obvious vertebrates. One type of life in the foreground. You see fungi in front of us, giant mushrooms that are actually the reproductive organs of the fungi that are living underground, and those are being colonized by ants. So you can see that we're standing on a mound of dirt. That is part of an ant colony. And then, of course, in the background, you see plants, and it would take a lifetime to name and categorize all of them. The point in showing this picture is that biologists in general try to organize their thoughts around what is life by establishing something called a phylogeny. And so this is the phylogeny of all life on Earth. We are all descended from a common ancestor that's shown at the very bottom of this tree. And as you go up the tree, right, organisms are branching off into different large units. And we classify different organisms into these three major groups: the bacteria, the archaea, and the eukaryotes. Don't worry, this is not a return to Bio 20 or whatever class you took at Brown. The reason that I want to show you this is because if I put this off to the side and I ask you, well, where is everything you can see in this photo? Where does that fit on this tree of life? It's all in this upper little right corner. Life is so incredibly diverse that all of the plants, all of the fungi, and all of the vertebrates in the world fit into just a teeny little few branches of the tree of life. Now, that's an incredibly fascinating topic, but as someone who came from history and then into geology and then into biology, it was just too complicated to worry about all these species. And so I entered a field where we look at things more holistically, in a more reductionist way, and we ask questions about what is common amongst all life. And that actually ends up leading us to a very interesting answer. So if you look, for example, sorry, let me just click here. If you look, for example, at our part of the tree of life, and you grind us up and you put us in an analyzer and you ask, well, what are we really made of? Like, what is it that makes me and Phoebe and this fungi? What you see on the bottom is a rough chemical formula of all of the organisms you can see in this picture. The H stands for hydrogen, the O stands for oxygen, the C stands for carbon, the N stands for nitrogen, and the P stands for phosphorus. And the little numbers underneath just tell you their relative abundance in our bodies, okay? And in the bodies of everything else you can see. What's so interesting about this is that if you go all the way over to the other side of the tree of life, into the bacteria, and particularly the cyanobacteria that I'm showing you here, these are organisms that under a microscope look like those little green dots, okay? And you look at their chemistry looks exactly like ours. Not exactly. The ratios are a little bit different, but the order of most abundant hydrogen, second most abundant oxygen, third most abundant carbon, fourth most abundant nitrogen, fifth most abundant phosphorus, that's the same across all life on Earth. So I would put to you, for the purposes of this talk, the first big idea is, if you ask what is life, life consists of organisms that must gather these 5 elements from their environment. Life is a constant struggle for these 5 elements. And if you succeed at getting them, you succeed as an organism. And if you fail to get them, you fail as an organism. And that's true in the short term, and it's true over evolutionary time. So let's take with us from this very brief vignette life as a bag of elements. Okay, reductionist, yes. Avoiding all sorts of complicated theological questions, yes. But for the purposes of this talk, life as a bag of elements, and specifically these 5 elements in this particular rather fixed ratio. And I want to use that understanding to think about the next question, which is how living things can change the world. In order to do that, we need to think a little bit about the composition of the surface of the Earth where we live. So this is obviously a picture from the International Space Station of our planet with its thin atmosphere. And I've already talked, I'm just going to minimize this so I can see my slides a little bit better. I've already talked about how access to these elements, how regulates how much life there is on Earth. So life is a constant struggle for these five elements. What I want to bring into the conversation now is how important these elements are, not just for life, but for the planet itself, or for the characteristics of the planet itself. Because it turns out, sorry, that four of these five elements, hydrogen, oxygen, carbon, and nitrogen, make up the greenhouse gases that regulate our climate. In other words, water vapor, carbon dioxide, methane, nitrous oxide, the gases that keep our planet habitable are made of the same elements as we are. Whether or not that's geologic happenstance or grand design or whatever you want to think of it as that's not the purpose of this talk, but it's important to know because there is now an important interplay between organisms on Earth that are struggling to gather H, O, C, N, and P and the gases that regulate the environment on Earth. So I will put out there as a starting idea for this part of the talk, for this vignette, that when life evolves new ways to gather these essential elements, it is inevitable that those organisms that have evolved new ways to do this change the world. And so in order to convince you of this, I'm going to take you through a very, 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 very rapid history of Earth, or history of life on Earth. And I'm going to tell you three examples to illustrate how when organisms evolve a new way to gather these elements from their environment, they can change the world. The first example comes from very deep in geologic time. This diagram on the slide right now can be thought of as a clock. The formation of Earth, can you see my cursor? Can someone just shout out if you can see my cursor?
Yes, see
Great,
it.
thank you. So the formation of Earth starts about 4.5 billion years ago, and you go around in time this way. So the formation of the moon is right around the formation of the Earth. By about 4 billion years ago, first life emerges, photosynthesis starts, all the way around to the evolution of vertebrate land animals, and all the way to this teeny line here, which is really too thick if we're going to be realistic, for the first hominids, the first of our ancestors. And the story that I want to tell you from this geologic time, the first story is a story of bacteria about 2.5 billion years ago. The second story is a story of plants about 400 million years ago. And the third story is our story. And I'll finish with that and move into the last part of the talk. So let's dive in. The first and biggest, most important world changers in the history of our planet are a group of organisms called the cyanobacteria. And their story starts really with the beginning of life on Earth, but plays out over the first half of Earth's history, the first 2 billion years or so. Now, that story is billions of years old, but human understanding of that story actually is kind of old within human history. And in order to illustrate it, I want to take you back not to 2 billion years ago, but to the late 1770s, around the time of the American Revolution. But this was not in the U.S. It was in Europe, and some work by a theologian chemist named Joseph Priestley in England. And he was really interested in the nature of air. He lived next to a brewery, and he was fascinated by the idea that if the wind blew or by the observation that if the wind blew from the brewery, the air was putrid and it was hard to breathe. But if the air blew in the other direction, it was pure. So he was interested in understanding the nature of pure and putrid air. And he did a bunch of really unbelievable experiments, and these are illustrations from his original publication. The first thing he did is he put a sealed bell jar around a burning candle. And what he noticed was that the candle invariably snuffed out. He then tried the same thing with a mouse and found, slightly more gruesomely, the same effect. But to his surprise, and amazement, but also his deep insight. When he put a mouse or a candle in with a plant, the mouse lived much longer. The candle stayed lit much longer. In his words, I found that the air would neither extinguish the candle nor was it all inconvenient to a mouse. I love that language. And from that, he concluded that air itself is not an unalterable thing. It took almost 200 years after Priestley wrote this in 1777 for us to begin to understand just how much the air had been altered over the history of our planet. And it's to that that it is for that reason that I want to return to 2.5 billion years ago. Because the bacteria that changed the world then changed the air in a way that nothing has ever done since. So let's talk a little bit about what air was like on early Earth. Like today, it was composed mostly of nitrogen. Our air that you and I breathe in right now is about 80% nitrogen. And that nitrogen consists of two nitrogen atoms bound to each other in a very strong bond that we and almost all other organisms cannot break. And as a result of us being unable to break it, we breathe that nitrogen out and we breathe that nitrogen in and we breathe it back out with no change. So like then, air was mostly nitrogen. And I'll just warn you, this next 4 to 5 minutes has some chemistry in it. I'll walk you through it very, very simply. And so if you see formulae and whatnot, I promise to explain them. Hang with me. It's only like 5 minutes and it'll be good. So the second and really important thing that I want you to remember about air on early Earth is there was no oxygen. So today, air is about 21% oxygen. Two oxygen molecules, two oxygen atoms bound to each other. Unlike nitrogen, which is tightly bound, those two oxygen atoms are highly reactive. They break apart all the time. And it's that breaking apart that we actually utilize when we're using oxygen ourselves. The early air, however, had no so-called free oxygen, these two oxygen atoms bound to each other. The planet was kept unfrozen by greenhouse gases, but in this case, the main greenhouse gas was not carbon dioxide, as it is today, but methane. Methane is CH4 for those of you who are interested. But really what I want you to understand about methane is that methane is rapidly consumed by oxygen. However, on the early Earth, there was no oxygen in the air. So methane that was put up there just stayed up there. It wasn't destroyed by oxygen. Today, when we put methane into the atmosphere, it breaks down relatively rapidly. On the early Earth, it did not. So if that's what air looked like on early Earth, what did life look like? Well, as today, life on Earth was made of the same stuff it is today: hydrogen, oxygen, carbon, nitrogen, and phosphorus. And it was all in the oceans and all single-celled organisms. So if you're a single-celled organism living in the ocean, you have lots of hydrogen and oxygen. Water, after all, is H2O. So access to hydrogen and oxygen was fairly simple. How did these organisms get carbon? They got it mostly, at least by the time this story takes place, they got it mostly from photosynthesis. And so I've shown you a reaction that may evoke a high school biology class. On the right-hand side, carbon dioxide plus, in this case, hydrogen sulfide plus sunlight produces organic material and sulfur. This is the early form of photosynthesis that was being used by most of the organisms on the planet. And there's two things I want you to realize about this chemical reaction. The first is that it's driven by sunlight. So it's using sunlight to capture elements like carbon from the environment and store it in organic material. This is what plants do today. But because it's using hydrogen sulfide, that is a fairly inefficient way to do it. And what I mean by inefficient is for a given amount of light, you can't capture a lot of carbon dioxide. You can't make a lot of organic material. You can't grow very much. So this reaction allowed life to exist fueled by sunlight, as plants do today, for example, but it wasn't as efficient as plants are today because it was using a primitive so-called form of photosynthesis. So life could easily get hydrogen and oxygen. It could get carbon through photosynthesis. What about nitrogen? Well, there was actually very little nitrogen in the early oceans, to the best of our ability to tell. And because nitrogen is an element that is really important for building the machinery that carries out photosynthesis, life in the ocean was probably limited by the amount of nitrogen. So think of it as, I don't know, you have an electric car, but you can't produce very many batteries, right? So you had access to sunlight, you had access to carbon, but you couldn't build enough machinery to sort of capture that stuff. Into this world of no oxygen in the air, inefficient photosynthesis, a limitation of the amount of life on Earth by nitrogen, evolve a group of organisms called the cyanobacteria. I actually showed you a picture of them earlier in the first part of the talk. And they produced two key evolutionary innovations to overcome the constraints of early life on Earth. The first is they evolved a new path of photosynthesis. So I'm showing you the old path on the left, carbon dioxide plus hydrogen sulfide, that's H2S, plus sunlight. That's the reaction that allows these organisms to capture CO2 and turn it into body mass, organic material. But cyanobacteria evolved a new reaction. And the only change in that reaction is that instead of taking carbon dioxide and hydrogen sulfide, H2S, instead they took carbon dioxide and combined it with H2O, with water. This is important for two reasons. First, they're living in the ocean, so there's lots of water available. But second, using this reaction allows them to build more body mass per unit of sunlight. This is a more efficient reaction. So the cyanobacteria are able to capture, for a given amount of sunlight, capture more material, build their bodies more. The other reaction that they pulled out of their evolutionary magic hat was an ability to take inert dinitrogen gas from the atmosphere, the same nitrogen you and I breathe in today, and transform it into a usable form, NH3. This is important because nitrogen was limiting the number of organisms in the ocean. And so by building a more efficient photosynthesis, the left-hand equations, and being able to pull nitrogen from the air, the right hand, they were able to not only build the machinery for photosynthesis, but use that machinery for an even more efficient photosynthesis. And so they began to wildly proliferate as a result of these two evolutionary innovations. In fact, we estimate that the amount of life on Earth probably increased by a factor of at least 10 because of this coupling of innovation. So access to energy in the form of photosynthesis and access to food in the form of nitrogen being pulled from the air spurred wild proliferation. And for 100 million years or more, probably close to 300 or 400 million years, the cyanobacteria kind of took over the oceans. But they accidentally they accidentally caused pollution that had nothing to do with their intention, and I put intention in quotes because these are single-celled organisms. So what do I mean by that? I want to return to this equation and focus now not on the more efficient carbon dioxide plus water, but the byproduct. When photosynthesis used hydrogen sulfide, it produced sulfur. But when photosynthesis used H2O, it produces oxygen. And after hundreds of millions of years and wild proliferation, the cyanobacteria pumped so much oxygen into the air that the atmosphere's chemistry began to change. And this brings us back to a key point, and the point that I highlighted earlier. The Earth at that time was being kept warm by a methane blanket that was able to keep water unfrozen under what was then a relatively faint sun. But oxygen reacts with methane. And as a result, this accidental pollution from the cyanobacteria's way of life, from their way of capturing carbon, from their way of capturing nitrogen, from the success as an organism that engendered, led them to accidentally pollute the atmosphere. And this pollution actually created a global environmental catastrophe. It produced an almost global glaciation, the first that we're aware of. It probably collapsed most life on Earth. And I say probably because everything at that time was single-celled and we don't have a great fossil record. But imagine going from a world that had no oxygen anywhere or just in teeny little places to oxygen everywhere. All of the organisms that were adapted to anoxic, that is no oxygen conditions, would have been relegated to the sort of obscure corners of the planet. Imagine if it happened today the other way. If we went from an oxygenated environment to an anoxic environment, almost all life on Earth would disappear. This inevitably changed the tree of life and shaped evolution in ways we cannot possibly know. And the key point I want you to take from this first long vignette before I give you one more short one is that this resulted from an organism that innovated, proliferated, emitted an unneeded pollutant into the air, and accidentally changed the global greenhouse. So that's the story of the bacteria. I want to jump forward now another 2 billion years to a scant 400 million years ago. And one of the things I love about geology is that when you start really thinking about the age of the Earth, 400 million years is actually fairly recent. I don't have a huge amount of time, and I don't want to take a huge amount of your time to tell this story. If you're interested in it, there's a lot in the book about it. But this is a story of land plants and their evolution from ocean-dwelling photosynthetic organisms to land-dwelling photosynthetic organisms. This transition occurred about 400 million years ago, so before the dinosaurs, but long after the bacteria and the oxygenation of the planet. 400 million years ago, the Earth looked actually quite similar to the way it does today in some ways. So the air was mostly the way it is today in terms of about 80% nitrogen, about 20% oxygen. There was carbon dioxide keeping the planet warm, so most of the methane had been destroyed with the oxygenation of the planet. Carbon dioxide was the main greenhouse gas. There were some differences. It was a very warm world that plants evolved into, so you could have swum at the North Pole without a wetsuit. And all of the continents were in the southern half of the globe, but by and large, all major forms of life that we see on Earth today were present at this time. Plants moved onto land under very warm, very high carbon dioxide concentrations in the atmosphere. And through a whole host of evolutionary innovations that I'm not going to talk about today, but I'm happy to answer questions about, essentially solve the puzzle of getting hydrogen and oxygen, carbon, nitrogen, and phosphorus on land. And that's actually a really hard thing to do because hydrogen and oxygen come mostly from water. And plants were now in a dry place and they couldn't walk around to look for water. So that's itself a fascinating series of evolutionary innovations. They also made some major changes to the way that they got phosphorus. Again, I don't have time to go into it too much. But the story that I want to tell you, or the brief story that I want to tell you about it, is that they solved, like the cyanobacteria before them, they solved the puzzle of getting these elements from their environment, in this case on land. And what do you know? They proliferated wildly. So the first land plants probably took 10 or 20 million years to get out of swampy areas and up onto dry land. But eventually, over the next 100 million years or so, forests stretched from the equator to the poles. And those forests pulled so much CO2 from the air through a variety of mechanisms, which again I go into in the book and I'm happy to answer questions about. But over that 100 million year period, from about 400 million years ago to 300 million years ago, these forests pulled so much CO2 from the air that they began to freeze the planet. They broke down the global greenhouse that was keeping the planet warm, and they caused an ice age that led to a mass extinction event, one of the 5 that we know about in the modern era of life on Earth. That environmental catastrophe occurred because an organism was able to pull these 5 elements from their environment and reshape the atmospheric greenhouse by accident. And it is their fossils, the carbon-rich plant fossils from 300 million years ago, that humans find in the form of coal and begin to burn and return to the atmosphere at the beginning of the Industrial Revolution in large amounts. So from that story of land plants who also accidentally uh, changed the planet after they succeeded in gathering these 5 essential elements, I want to now fast forward to the third world changers, us. So it's unquestionable that we are wildly proliferating. Here's a graph for the last 10,000 years of human population, and we will taper out to about 10 billion people by the middle of this century. And so one might ask then, in this era of what we call unprecedented environmental change, why are humans so successful? And I would argue that it is largely because we have mastered, uh, like our world-changing predecessors, the ability to capture these 5 critical elements from our environment. So what do I mean by that? Well, for hydrogen and oxygen in the form of water, we now store 3 times more water in human-made reservoirs than exists in all of the world's rivers combined. We have dug up the carbon and therefore stored energy of old plants, and we are burning them for energy at a rate of about 1,000 years of global photosynthesis, preserved as fossils, per year for our energy source. Not the energy of our bodies, and so that's a big difference between us and our world-changing predecessors, but energy for our industrial society. We use the energy from fossil carbon to get nitrogen from the air. We have become the only multicellular organism in the history of life on Earth to be able to pull nitrogen from the air and turn it into a usable form. We do that through an industrial process called the Haber-Bosch process that allows us to make fertilizer. And without that, we could only feed about half the number of people that are on Earth at the moment. What about phosphorus? I didn't tell much about this land plant's innovations with regards to phosphorus, but similar to them, we use energy to mine phosphorus from the earth, from the rocks in which it is housed. And we actually pull more nitrogen from the air and mine more phosphorus from rock than comes from the air naturally or is mined from rock naturally across the entire world. So we pull more nitrogen from the air than all other organisms combined, and we mine more phosphorus from rock than all of the land plants in the world combined. And as with our world-changing predecessors, we are causing unintended consequences. So before I talk too much about how we might think about sustainability, I do want to make sure that I impress upon you the importance of the changes that we're making. But I also want to impress upon you that solutions are at hand. So while the next few slides are going to be a little bit scary, I think, although certainly probably not unanticipated, I want you to understand that the last part of the talk is really one that is about the opportunity we have to fix it. So the first and of course most apparent change that we're making is our accidental emissions of CO2 are warming the planet. And I say accidental because we have no interest in putting CO2 into the air. We only want energy. But our method of getting energy is releasing carbon that was stored hundreds of millions of years ago back to the atmosphere. So I just want to give you a sense of how rapidly the world is changing. And in order to do that, I always show these 2 slides. Um, and I feel like they need to be embedded in everybody's brain as we think about the issue of climate change. So this is obviously a map of the planet, but it's color-coded in a very specific way. The colors tell you, for a particular time period, whether a particular place was warmer or colder than it usually is. So let me explain what I mean by that. The time period here is 1880 to 1884. Let's look at West Africa. The hot colors here mean that West Africa, during the time period 1880 to 1884, was about 1 or 2 degrees Celsius warmer than West Africa was in the middle of the 20th century. In contrast, if you look at Western North America, at that time period, 1880 to 1884, Western North America was actually colder than Western North America was in the middle of the 20th century. So all of these colors are showing you whether the place was hotter or colder than its mid-20th century temperature. And what I'm going to do now is run this video forward in time. So now we're going through the 1880s, and just pick a place and watch it. It's kind of cool. Right? And then try and see if you can see a change. So you can see a lot of places getting hotter, a lot of places getting colder. This is what we call natural variability. We're now into the 50s and 60s, and 70s and 80s and 90s and 2000s. And here we are up through 2022. This is the accidental change to the planet. When we talk about a 1.5 degree or 2 or 3 degrees Celsius rise as a result of climate change, this is the manifestation of that at the global scale. Yes, there is variability. Yes, there is more warming in some places than others, but there is no place that is really cooling. But there's more to it than that. What I've shown you just now is the average temperature of the planet, but a lot changes when you change the average. So here is a different way of looking at those same data. This is a histogram. So what this is showing you is in 1964, in this particular case, and I'll show you a video going through the present, for every parcel of land, some of those parcels were about their average temperature, so neither red nor blue on the previous map. Some places in 1964 were colder than they usually are, and some places in 1964 were warmer than they usually are. And what I showed you in the previous slide was that this peak, this average temperature, is slowly shifting to the right. But humans don't experience and care much about the average temperature. The Earth system does, but humans don't. You don't walk outside and say, oh, wow, it's 61 degrees, not 60 degrees. You care about the extremes, right? And so what I want you to watch in this video that's going to run from 1964 forward is not the shift in the average, although you'll notice that too. I want you to look at the number of places on Earth that are in the extremes, the extreme cold and the extreme warm. So here we go forward in time, 1965. And you can see the average bumps around, and sometimes you get some hot, sometimes you get some cold, and that peak is shifting, and it's shifting to the right as the average temperature gets warmer. But look at the far end. The number of places that are extremely, unusually warm for them. That is almost half of the world being more than 2 degrees Celsius warmer than it usually is. And some places 4, 5, even 6 degrees Celsius warmer. This is the climate change that we are living through with extreme droughts, with extreme heat waves, with dramatically rapid ice loss, etc. It's not so much the shift in the average that matters. It's the shift in the extremes. So if those changes are the unintended consequences of our success with carbon and energy, let's talk a little bit about our overwhelming success with nitrogen and phosphorus. Without nitrogen and phosphorus fertilizer, we could not feed ourselves. And yet our overuse of this fertilizer has consequences for air, water, and health. Too many to go through right now because I do want to talk about solutions. But just to give a few examples, fertilizer runoff from our major agricultural areas, shown here in green, fuel dead zones where multicellular life cannot exist along our coasts. And a host of other problems, including climate change and drinking water problems and acid rain and ozone depletion and smog. Lots and lots of things come with fertilizer use. I talk a lot about it in the book. I'm not going to go into it now because now I want to switch from gloom and doom to possibility. And in order to do that, I want to start by talking about what it really means to be sustainable. And of course, in this day and age, if you want to know anything, you have to ask ChatGPT. So I asked ChatGPT to write one sentence for a definition of sustainability. And it said, sustainability is the practice of meeting the needs of the present without compromising the ability of future generations to meet their own needs, which is a perfectly good, if somewhat vacuous explanation, which is what ChatGPT is good for. What I would posit and what I do posit in the book is that sustainability really starts with the wise management of life's 5 essential elements. And I'm going to give you just 2 examples before I wrap up of what I mean by wise management. So let's start with carbon. Our climate change problem is a result of our accidental release of carbon dioxide as a result of burning fossil fuels. And we burn fossil fuels for energy. So one question we could ask is, well, could we possibly get the energy we want without the CO2 emissions that we don't want, right? The cyanobacteria could not do that. Every time they needed something, every time they built another cyanobacterial body, it pumped out more oxygen. The plants couldn't do that. Every time they had another tree, it sucked up more CO2 out of the air. But we, because the vast majority of the energy we use is outside our bodies for the society that we run, not for the bodies that we run, we actually have the opportunity to decouple our energy supply and our CO2 emissions. And I'm going to give you a very personal example. This is my house, and this is my car, circa 2007. It's actually not my car, it's my neighbor's car because didn't know I was going to give this talk and I didn't have a picture of my car. Anyway, so this is my house before I got tenure. I didn't want to paint it because I was afraid I wasn't going to get tenure. Whatever. We didn't do any renovations. We just kind of lived in it and hunkered down. But then I got tenure and we decided to do a renovation. And what we did was essentially an energy retrofit on the house. So um, we changed the insulation, etc. So let's talk about the 2007 house to begin with. In order to keep our house warm, we burned about 866 gallons of oil per year in a big old furnace that's out in the basement. Our car, if we were an average American, burned about 600 gallons of gasoline per year to get around. And to run our fridge and to run our TV and our computers and our lights, etc., we used about 3,400 kilowatt hours of electricity per year. All of that cost us about $6,700 in energy costs and emitted about 15 tons of CO2 to the atmosphere each year. We didn't want to emit the CO2. We wanted a warm house. We wanted lights. We wanted mobility. So after I got tenure and we did our energy retrofit, we got rid of our furnace. We switched to heat pumps. We got rid of our gas car. We switched to an electric car. So let's look at the numbers from that. So here's the new house. Okay. Yellow. I've always liked a yellow house. Here's the new car. That house uses no oil. It's only heat pumps. So they run on electricity. That car uses no gas. And as a result, we use a whole heck of a lot more electricity, roughly 4 times as much electricity. It costs us about half as much as having fuel oil delivered per year. But because using electricity is so much more efficient than burning stuff, even though power plants in Rhode Island are running mostly on gas, even counting the emissions associated with generating the electricity we consume, our emissions drop to 3 tons a year. Okay, so that's a 5-fold decrease, or however you want to say it. It's a 80% decrease. Our house is warmer and more comfortable than it used to be. The car drives better than the old gas car. We have air conditioning in the summer, which we never had before. We have all of the things we wanted out of our house, but not the emissions. And by the way, also not the expense. Of course, on a net basis, we could do better. And so 2 years ago, we put solar panels on the roof. And so now we actually generate on an annual basis as much energy as we consume. It's not perfect yet. It's not 24/7. It's coming, right? But nothing about our house, everything about our house and our car is better than it was before. We've decoupled our energy from our emissions. So you might say, well, look, that's one house that can't work globally, whatever. And this is why I say this is a moment of hope. Because really the answer to climate change is very simple. It's electrify everything and get your electricity from non-emitting sources. And I want to go to many of your home state as another wonderful example. This is a graph showing you the California electricity grid and its load and its supply of electricity from midnight, 12 a.m. to the next midnight. This happens to be from May 2nd, but this pattern held true for 132 days in 2024. And what it's showing you on the y-axis is the fraction of electricity, in California the fifth largest economy in the world, that comes from solar, wind, geothermal, hydro, and batteries, not from fossil fuels, just from renewables and batteries. And what you can see is that from roughly 8 a.m. or 9 a.m. through to the end of the day, renewables on this day are providing more than 100% of California's electricity demand. And even at night, they're providing 50%. This happened for 132 days in 2024, and it will continue to happen for more and more days every year. This, for example, shows you the incredible change between 2024 and 2023 and 2024. So this is California electricity, the fraction that is needed, produced from wind, water, and solar. And you can see from February to June in this graph that in 2021, 2022, 2023, there was between 40 and 80%. And then look at 2024 and look at the increase across 2024. The deployment of solar, the deployment of batteries, and the deployment of wind is changing the world really, really fast. If you look at Europe, the same thing is happening. So here is some data on the left from 2011 through 2024. Look at the drop off in coal. And in 2024, solar surpassed coal across all of Europe in terms of electricity production. Gas is declining as well. Even nuclear is declining. What's going up? Solar. What's going up? Wind. Batteries are coming online, and the fraction of fossil fuels is dropping. We can do it on climate change. We can fix this. We have the technology that we need. It's just a matter of deployment. I'm going to give you one last example before I wrap up. Oh, and I'm sorry I'm already at 51. My apologies, but I'll stay it a little bit longer for questions if people want. This is an example of how we can decouple the problems that come from our overuse of fertilizer from the benefits we get from all the food we make. And so the question here is, can we get the food we need without the consequences of fertilizer pollution? I'm going to introduce you to my friend and colleague and one of my idols. Her name is Lisa Schulte-Moore. She's a professor at Iowa State. And Lisa had a really brilliant idea several years ago. She was trying to understand how she could transform Midwestern agriculture, the corn and soy agriculture that fuels so much of the American economy. I would say it provides a lot of food, but mostly it provides food for animals, and that's another talk. But Lisa wanted to understand how she could continue that production system without the environmental consequences. And she had the idea of something called prairie strips. So what you're seeing is an air photo of a farm in Iowa. And these multicolored curving strips are native prairie grasses that are planted on between 5 and 10% of the farm, but in a very specific orientation. And that orientation is perpendicular to the way water flows. So water would flow from the top right down to the bottom, and that means that all of the soil that's eroding away from the soybeans that are shown here in the dark green color, that gets trapped in these prairie strips. And if you go down to the very bottom of the watershed, down here off the left corner of the farm, and you look at the experiment that she created, you see some really remarkable results. So on the left is water flowing out of a cornfield, 100% crops. On the right, you're seeing water that is flowing out of a field that is 90% crops and only 10% prairie. And look how clear that water is. It's not quite as clear as the water coming out of 100% prairie, but you're getting 90% of the corn, or maybe even a little more, with very little of the downstream problems. In fact, nitrogen loss and phosphorus loss and soil loss is decreased by between 70 and 90% where these prairie strips are implemented, and they're being implemented all across the Corn Belt. There's 18,000 plus acres of prairie strips. Every time I give this talk, I have to re-update because it's exploding. There's over 180,000 acres of cropland across 14 states where Lisa's idea of prairie strips are being integrated into industrial agriculture, solving the problem, or at least mostly solving the problem of nutrient loss, while preserving the benefits that we get from our manipulation of nitrogen and phosphorus across farmland. So, to wrap up, really what I want people to understand and think about is that we can build a sustainable future based around the wiser management of life's five essential elements. We are, after all, living in a bell jar. The earth is a bell jar, just like Joseph Priestley's bell jar. And it is possible for us to live in a way that is not inconvenient to us or to other organisms on this planet, as long as we consider what we are doing with life's essential elements. We can do it. So with that, if you're interested in the book, you can scan with your phone this QR code or just look it up. I will stop sharing my screen. I apologize for going a little bit longer than I anticipated, but I would be, oh, you already got it. Wonderful. But I would be super happy to take any questions. I see there are some questions in the chat. So maybe I'll start with those. Hey, Emily. Um, okay. What happened to the O in early photosynthesis? So Emily, I'm sorry, I don't quite see what your question was.
So it looks like it's Marlena has a question about
Oh, okay.
it.
Okay,
Yes,
Marlena
you
submitted a
mentioned
question.
one of the, it
What
was
happened?
with the hydrogen sulfide photosynthesis.
Yeah.
So there's an O in there, right? It's carbon dioxide, yes. And then what's happening to because the O really matters later on, for the
Oh, I see
cyanobacteria.
what you're
What's
saying.
happening
So,
with the
so
oxygen?
yeah, so the O in the carbon dioxide is not being released to the atmosphere. It's being incorporated, like it's it's either being incorporated into the organism or it's reacting with other things. And so like it's not, yeah. So that's a good point. That's a good question, but that's mostly being used in the internal metabolism of the organism.
Okay,
Yeah, good question.
yeah. By the way, I just want to say I listened to your book. I really enjoyed it. So
Oh,
I'd recommend
wonderful.
it to folks.
Thank
Yes.
you. And Dan says, isn't the release of CO2 not an accident? For example, melting of the Arctic opens new shipping routes. Yeah. So what I would say about that is that nobody nobody set out to melt the Arctic by emitting CO2. We set out to provide energy for people. And by the way, fossil fuels have provided enormous benefits to us all globally. We've raised billions of people out of poverty. We have access to medicine that is unimaginable in the pre-fossil fuel age. The access to that energy has provided a huge amount of benefit to us. The problem is that it comes with this unintended release. Now, you could also argue, of course, that there are some people who don't care about the release, some people who are making a lot of money from oil and don't want to change. But if they could continue to sell you oil and have it not emit CO2, they'd be perfectly happy to do that, right? It's not that the goal is to release CO2. The goal is to sell stuff and get energy from it. And the release of CO2 is sort of an unfortunate chemical problem. And so I don't, I, and then the second part of the question is, how do you see these consequences being mitigated when the related causes are encouraged by current? So I would say that, and we had this a little bit of this conversation, Lisa and I, before. I don't think I don't think it's likely that anyone is going to give up on their business. And like, I don't think Exxon is going to say, you know what, we'll just leave it all on the ground, forget the trillion dollars of capitalization of our company, like whatever. But you know, the horse and buggy industry was really big until the car came along, and the landline industry was really big until the phone came along. And what we're seeing in liberal places like California and conservative places like Texas is that almost all new energy generation coming online is wind and solar and batteries. And that's getting cheaper and cheaper. And China, for example, is just this year decreased its oil imports for the first time in decades because they're electrifying their vehicle so fast that their vehicle fleet so fast that they don't need more oil. And so these trends are happening, and the real rate there's no doubt in my mind that that there will still be people driving gas cars for a long time, just like there are still people riding horses, but it won't be a problem. The question is, can we make that transition fast enough to avoid the consequences? And that is a very open question, right? It is what's really encouraging to me. So I've been doing this I got to Brown in 2007. I would say that I'm more optimistic now than I was in 2007. And the reason that I'm more optimistic now is that we actually know we have all of the technology, or let's say 75% of the technology we need to fix this problem. And in 2007, we had exactly none of it. So, you know, do we have the political will? I don't know. That political will varies by region, of course, right? But in 2007, it wouldn't have been possible even if we had the political will. And now it's possible. And so that's changing things. And, you know, like the fact that EU's, like California's gas consumption dropped 40%, gas consumption for electricity dropped 40% in 2024. That's a huge jump. Europe's gas consumption also dropped, right? So, and their coal consumption also dropped. These are big economies. China, its coal consumption is still increasing, but it's very likely to turn the corner in the next couple of years. And China installed more solar last year than the US has in its entire history. So, like, these changes are happening. Australia, South Australia is going to be 100% renewable 24/7 by the end of this decade. Like, it's coming. It just, it's whether it's like a race against time, right? And this is why, like, every day, this is the fight I fight. And we all need to be fighting the fight in whatever way we can. But, like, this is, there's opportunity now, whereas there was only wishing in 2007. Okay, so Emily, did not expect AI to enter a valence I had not considered. How are you able to make these calculations? Can you just tell me, Emily, what you're asking so I can answer it more directly? Can't hear you still. You're unmuted, but for some reason we can't hear you. Mm-mm. Okay, while you figure that out, I'm going to go on to the next one and then you can come back. Also in California, new building codes requiring all new to install heat pumps instead of gas furnaces. Yes, that is great. Dan Epstein, Dan says the cost of Lisa. Actually, so Dan, your question about Lisa's prairie strips is really interesting. The cost is minimal because they tend to put it on the least productive land. All farmers have some land that is less productive than others. And then the other thing that's really interesting is that even if there is a small cost, the boost in wildlife and sort of prettiness and is very appealing to farmers, so they're willing to take that cost. They're also able to use prairie strips in what's called the Conservation Reserve Program, which is a federal program to encourage conservation on farmland, so they get payment for that. And then the last thing is that all farmers in the Midwest are very concerned about soil loss. So the joke in Iowa is, where's the best soil in Iowa? And the answer is the Gulf of Mexico. And the reason is that they've had about 16 inches of the best soil on the planet, and they've lost about 8 of those inches in the last century through erosion. And prairie strips allow them to rebuild soil because you can plant the prairie strips, leave them for 5 years, mow them down, plant corn there, and move the prairie strip just uphill a little bit or downhill a little bit. And so you have this incredible opportunity to rebuild soil. And when you talk to farmers in the Midwest about building soil as opposed to just stopping the loss of soil, that's an incredibly important thing. So the cost is quite small. And she actually, the limitation to deployment of prairie, and she won a MacArthur Genius Award for this. Like she's an amazing person. The cost to the farmer is actually pretty minimal, and the deployment is only slowed by the fact that the teams can't get out there fast enough to get it done. And some really big, like Smithfield Farms, which is one of the biggest hog producers in the country, like they're putting it across all their farms across all. I mean, it's a really interesting idea. I think one of the things that's so important about this topic is that it's really easy to get down and depressed and worried and anxious. And there's so much good news that doesn't get reported because it's not good clickbait. And like we're making a lot of progress. That doesn't mean we don't have huge challenges and we don't have big things to do. I'm not Pollyanna, but I do think that there's a lot of good happening. And if you're interested on the climate space, there's a fantastic climate scientist named Catherine Hayhoe, and she sends out a newsletter each week with the good news, the not so good news, and the bad news. And I think that's really useful because it isn't just all one thing. And actually, we're turning corners left and right. And again, it's not just like liberal California mandating that you can't put in gas furnaces. It's Texas and their libertarian approach to electricity market that is leading to more rapid deployment of renewables and batteries than even California. So it's kind of interesting across the political spectrum. All right, Emily says, who's in charge of the levers behind the changes? Which Sorry, Emily, I still don't know which changes because I've talked about a lot of them, but let me just read. Oh, and AI. Okay. So let me answer what I think is your AI question as best I can. So AI is incredibly computationally expensive and uses a lot of electricity. And so just like Bitcoin before it, where if you go back 10 years, you'll see all sorts of news articles about how Bitcoin mining is going to cause a huge spike in emissions because we're going to need so much power. And that actually turned out not to be so true. Um, with AI, it's also certainly true that it's incredibly computationally intensive. It's also really, really young. So it's unclear to me that it's going to stay as computationally intensive as it is. I'm not a computer scientist. I would say two things about it. Like many tools, AI is going to be both horrible and wonderful at the same time. And with regards to climate, I'm not really sure what the net effect is going to be. I mean, Microsoft did an experiment with with Livermore or one of the national labs where they scanned through uh, 30 years worth of research on battery materials in 2 weeks. And so they were able to come up with hundreds of novel potential game-changing battery technologies using AI, right? That would have taken another 50 years for the scientific community to do by itself. So if that pans out, it would definitely be worth burning some fossil fuel or whatever to run that AI, right? And I think that's going to be true in ways that I'm definitely not smart enough to anticipate, and it will be a game changer for sure. I think the most recent estimates that I've seen is that AI will in no way compete with vehicle electrification or with home heating electrification in terms of electricity consumption. So yeah, we're going to have to triple the amount of electricity or even quadruple the amount of electricity we produce. And that will include AI. And that's something like a 10% boost, maybe, right? But the real big ones are the electrification of transport, the electrification of home heating, the electrification of industries. And those are going to be way bigger than the AI electricity footprint. And if we can do it for all those others, we should be able to do it for AI too. So I'm a little less worried about that. It's not, even at its biggest, it's not going to be that big, I don't think. And if we can figure out how, in the short term, it will definitely be a problem. Like it's putting strain on grids right now as as companies are building data centers. But that's only presaging the strain that's going to happen when we all electrify our vehicles, and the utilities need to be working on this. We as a society need to be working on this, and AI will add to that, but not in a way that is like, 500%. It's a 10% change, not a it's a that sort of thing, not even an order of magnitude. Uh, okay. Does anyone else have questions or thoughts or comments?
I have
Yeah,
a question.
oh, go ahead.
Well, it's a fight. Are you planning another book for the general audience?
We were
Might
talking
be too
about this, but
soon, huh?
yeah. So I mean, the honest answer is, I think I put everything I knew into 240 pages. So I don't want I have to live another lifetime. I spent a lot of time talking to the general public and writing things like op-eds and short essays. The book was kind of an experiment for me, and if I have something to say, I guess maybe I would consider it. But I have sort of dedicated my career starting in about 2016 to fixing the climate problem. And that's what I sort of live and breathe and do on a daily basis. And I will do whatever gets the most bang for the buck. And I'm not sure another book is what will do that. if it would, I would write it. But you know, we are in a real race against time, unlike any other in human history. And I sleep best at night when I am doing what I think I am most effective at. And that's usually talking and trying to come up with innovative solutions at the interface of science and policy. And I'm not sure that a book
Okay.
gets me there. We do run a podcast though, if you all are interested. I'll put it in the chat. It's student reporters from Brown, overseen by a professional staff, including myself and an NPR reporter. We're on in 20 states. These are teeny little bite-sized sustainability science. It's called Possibly, and the website is called askpossibly.org. We've produced over 250 episodes. And as an aside, since you're all alums, if anyone is looking to support Brown undergrads at the interface of science and society, and they're all going on into great journalism jobs, we are looking for some way to keep this going. We've been going for 5 years and we're sort of low on funding. So if you have any friends or you want to help Brown students do this awesome thing, they're heard on NPR every week during Morning Edition and All Things Considered in 20 states. So tell your friends. That's my little beg. But anyway, it's a great show. It's really fun, and the students do an awesome job.
Well, that's a great pitch. Maybe your next iteration is going to be Elemental, the TikTok dance, something like that to get the messaging going.
I can't. I would do it, but TikTok might be banned. You know, it just
Blue
depends on.
Sky, we've got you here. But yeah, I think in honor of our time, I have questions, but I just really want to thank you so much for your time on a Sunday, sharing your knowledge and a little bit of Brown with us.
Thanks for
Um,
inviting me.
yeah, I really enjoyed the book in the sense that you had three parts, but to me, the first part was a history, like a Ken Burns history. The second part was like a detective story, like how did we get here? And the third part was just kind of self-help, like how do we have solutions here. Why don't we take advantage of what we can? So if you haven't read the book, I really encourage you to check it out or listen to it. And I assume that you are reachable from your Brown email
Yeah,
for
please send
follow-up.
me an
So
email if you're in town. Let me know. Get coffee. I live and breathe this stuff. I love talking to people about it, as you can tell, I hope. And so really happy to continue the conversation. If you have questions or any ideas or thoughts, just reach out. Happy to.
great. Thanks so much, Professor Porter. Talk
Oh,
about
thanks so
climate
much,
change.
everybody. Have a great rest of your weekend. Bye
Bye
bye.
now.